Hello everybody, welcome back to the third lecture. This is actually the second time I'm recording the third lecture because after I finished the recording, I realized that I wasn't using the correct aspect ratio, which may cause the loss of quality on YouTube. So I was using the default settings of the Camtasia that captures the screen and also the web camera I'm talking to you. That setting was not good. Okay, anyway, hopefully you will get a better video quality from this lecture. Today we're going to talk about two topics. There will be 4 video clips. The first 2 will be on series connection, and the series connection we have the equivalent impedance and the voltage division, and for the last 2 clips would be the parallel connection, and that will also have the impedance, admittance, and the current division. And today's lecture is built upon the concept of the KCL, KVL, and the element constraint that we talked about last lecture. Make sure you have this concept solid grasps. Let's get started. So the first, let's look at what is the series connection. The series connection, if there are 2 elements, they share the same node without additional elements sharing the same node, then we see these 2 elements are connected in series. So let's take a look at the example. We have, let's see the first picture here. We have Z sub 1 and Z sub 3. Are they connected in series? And this one and this one, they share the same node, right? But in the meantime, this node is also shared by Z sub 2 and Z sub 4, therefore they are not connected in series. Now let's look at the second one, and we're asking whether Z sub 2 and Z sub 4 are they connected in series. They share the same node, and this node is not shared by any additional elements, therefore they are connected in series. Okay? Simple, right? So let's look at the equivalent impedance concept. So here we have n impedances connected in series. If you check Z sub 1, Z sub 2, they share this node and without additional, so on and so forth. So Z sub 1, so in this case we have Z sub 1, Z sub 2, Z sub n connected in series. And we would like to find the equivalent impedance. So first let's see what's the VI characteristic for this one, and we can write the element constraints. So the element constraints for the figure on the left are V1 is equal I times Z1. V1 and I are following the passive sign convention. So we have V2 is equal I sub 2 times Z2, and we can do this for this Vn. That's going to be equal I sub n times Z sub n, right? So these are the element constraints, but we also have the connection constraint, which is the KCL. KCL will require I equal I2 is equal to I sub n, right? Because at each node, you apply the KCL, you have I equal I2, and the inner current I is equal leaving current I2, and so on and so forth. And also based on the KVL, if we follow the clockwise direction, and we have V, the total, this is the voltage rise, that will be the sum of the voltage drops. So that's be V1 plus V2 plus plus Vn, right? And if we substitute this into the I, if we replace the I sub 2 and I all the way to I sub n by I, because the KCL, and then we collect the terms, so this will give us Z Z1 plus Z2 plus da 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 plus Z sub n and times I, right? So that's for, so this is for this one here on the left, on the right with the equivalent impedance on this one here, the V and I. This is easy, V and I following the tacit sign convention for Z sub EQ. This is equivalent impedance. And this equivalent impedance, we have V, this is going to be ZEQ times I. And therefore, in order for these two to be equivalent, we have the same VI characteristic that will require ZEQ. So if we compare these two, and we will reach, therefore the equivalent impedance should be ZEQ should be equal to Z sub 1 plus Z sub 2 plus da 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 plus Z sub n. Right? So that's the equivalent impedance for series connection. Then in the next clip, we're going to look at the voltage division for series connection. See you in a moment.